Hi folks, welcome back to Physics with Captain Rod. Making this video here to just provide an example here of how to do two-dimensional force and moment problems. So what we're looking at, we've got this L-shaped structure here connected by this what looks like quarter circle thing here. And what we're going to do here is we're going to work on calculating the reaction forces occurring at A, B, and C. So I'm going to start this with a free body diagram of this part of our system here. And in order to do that, what I'm going to do is cut it. Paste, put this off to the side. And start drawing force vectors on it. So the external loading here, we've got an 800 Newton meter counterclockwise couple moment. We've got this 400 Newton force down. All right, reactions at C. Well, C can support force reactions both horizontally and vertically. So I'm going to go ahead and put a CY on there and a CX. And this probably will have a CX because even though there's no horizontal loading along here, there's a force interaction between A and B that I'll talk about here in just a moment. So we've got our CX, our CY, the external 400 newtons, and the external counterclockwise 800 Newton meter. Now, my free body here, I also need to consider what's happening here. There's a pin here, and that pin is going to put a force onto this structure, and that force is going to be in a direction kind of up and right. Now, normally what we would do is we would draw that in component form. So I might start this with maybe a BX, BY. Now, if I kind of glance my free body over, you'll notice there's two unknowns at this location, and there's also two unknowns at this location. So at this point, this picture has four unknowns. And there are only three equations we can write for the free body. We can write force equation x direction, a force equation y direction, and we can write a moment equation. But that's not going to be enough to solve it. So as it sits here, this free body is indeterminate. That's what's called statically indeterminate. Now I'm going to go back and kind of investigate a little more what's happening at this intersection. So I'm going to take a look at this piece right here. This piece has a contact here and here, and that makes this piece a two-force member. When you have two force members, the two forces have to be equal magnitude, opposite direction, and they have to run right through one another. Their lines of action have to be right on top of one another. Otherwise, the member would have a net moment. So that tells me that the force direction at B lies along that path that I'm just erasing now. The force direction at B lies along this path. So I'm going to go back to these unknowns here, and I'm going to get rid of them, the BX, BY, and replace them with a single force vector in a known direction. And I'll just call that force vector B. And that force vector, again, needs to lie along this line of action because this is a two-force member. And that means, looking at this picture, 1 meter, 1 meter, that means that this is a 45-degree angle here. So I'll go ahead and list that in my free body. So here's my free body of the entire system. It should be solvable now. I'm going to go ahead and write a moment equation about C. Sum of all moments about C equals 0, counterclockwise positive. Now, moment equations, you always get to choose your point. I'm choosing this point because two of my unknowns go through C. This should allow me to write an equation to solve for the reaction at B. So summing moments about C, and I'm just going to start here and work my way outward. These two forces produce no moment about C. Right? This guy does, however. The moment produced by the 400 Newton force is going to be plus 400 newtons times the distance of 2 meters. Okay. As I move over to here, we see this counterclockwise 800 Newton meter couple moment, so plus 800 Newton meter. Right, now we got to take the effects of this force into account. Now I'm going to think about this in component form. BX would point this way, BY this way. the moment produced by Bx is counterclockwise, so I'm going to put plus Bx times, and then the moment arm for Bx lies or acts all along this line. The moment arm is this distance, looks like 1 meter in my picture. Right? Ooh, and you know what I'm going to do here is in the place of Bx, I'm going to go ahead and write that as B times the sine of 45 degrees. B times sine 45. And I'm doing that so I don't end up with two unknowns in this equation. If I use Bx and By, I'll actually end up with Bx and By in this equation. I want just one unknown. So I'm going to go ahead and write that Bx as B sine 45. All right, the By now is producing clockwise moment about C. So we're going to have minus. Magnitude of By is going to be B times the cosine of 45 degrees. And the moment arm for By is this distance, which is 3 meters. And I think that's it. I think that those are all of the forces and moments taken into account for a moment equation about C. So equals 0. So what I'm going to do now is wait for my helper here to calculate a numerical value for B. And I think what I'll do is pause it while I wait here. All right, so I'm back, and I'll just leave the control. I guess we'll get rid of it. We're back here, and we got 1,131 newtons for the magnitude of the reaction force at B. It came out positive, so it means the assumed direction there is looking correct. All right, so Cx and Cy. Cx can be had fairly easily. Force equation x direction. Might as well just do a standard right positive. So looking at our free body here, we've got this force, the x component of vector B. And I'm going to go ahead and just write that as 1,131 newtons times the sine of 45 degrees. And then this is not a force. This has no x component. Right, minus Cx equals 0. So Cx is going to be 1,131 newtons times the sine of 45 degrees. I'm going to wait for my good help here to give me a number. Around 800 newtons. That came out positive, which means the assumed direction is correct. Cy we can get several different ways, a force or moment equation. I'll go ahead and write another force equation. Sum of all forces in the y direction equals 0. I'll go ahead and keep the standard up positive. So that's going to be plus By, which is adjacent to this 45-degree angle. So that thing is going to equal 1,131 newtons times the cosine of 45 degrees for By, minus 400 newtons for this external load here, plus Cy equals 0. So Cy, again, I'm going to wait for my helper here to give me a value. It's going to be 400 newtons minus 1131 cosine 45. Negative 400 newtons. Minus sign just means opposite direction shown. Do not change it. If you go back and you change this in your free body, you'd have to go back and change, plus and minus signs in all your equations and work. Anybody that knows this stuff, when they look at this, they'll interpret that as right opposite the direction shown in the free body. So that's now a known value, no problem. All right. So we have the reactions at B now. We actually have B and C are nailed down, and the only thing to do now is point A. So I'm going to go ahead and get point A from a free body of this now. Now I also could do a free body of the entire kit and caboodle here, where the internal reaction here is, or where the reaction at B is an internal force. But rather than doing that, I think I'll just define this as my new system. Now, anybody that's watching this, if you need this stuff, you'll have to copy it down, but I need some room, so I'm going to get rid of these previous equations that we no longer need. All right, so now the reaction at B, we have this reaction up and right at point B here, By Newton's third law, that reaction is down and left, acting on this guy. And then we have a force reaction at A. And rather than putting an AX and an AY, I'm going to go ahead and just do this. I'm just going to put that force vector here and call it force vector A. These have to align, both force vectors have to lie on that line of action. And I'm just going to do sum of all forces in this direction equals 0, which means this force vector that I'm calling A minus B is equal to 0. So the reaction at A is equal to B, and I don't remember what we had, 1131? So that's 1131 newtons, and I'm just going to put in a direction like this, 45-degree angle. So we have the reactions everywhere on the structure. I hope this video helps demonstrate how to draw different free bodies and apply force and moment equations. Have a great day.